Today, thank you again to be here. Now, today we will start with, I would like to say, a couple lectures dedicated to model predictive control, which is a technique, a control technique, an optimal control techniques. In this sense, I thought that could have a place also in this course. Moreover, as you know, I am a control guy. This means for me, everything which is dedicated to control is extremely important, but we can consider also this technique in the context really of a more general optimization course. We will see the concept of convexity, cost functions, will appear again in a prominent form. The presentation which is in my study looks like, let me open, something like that. For the organization of the rest of the course, as I told you before, I will recover the lecture of last week at the end of the semester. This means we will prolong the course. We will include also another week, but anyway, we can do directly per Zoom. It could be that I'm here, but in any case, I have to do because you are right, to have all lectures, but also I think to complete what complete is a strange concept. But anyway, in accordance with what I have in mind, in any case, I need to use another lecture. Also, to discuss with you, we can do also per Zoom the project or something like that. We will see. Okay, this is the lecture of today. We can see introduction to model predictive control. We will see that what I will tell you is enough. Is enough to apply. Here in this presentation, we have three techniques, probably also more if I consider some small variations. I think that I will dedicate it, I will present all three techniques, but I'm not sure if I will show you all three simulations. I will upload all three simulations, but it could be that I will explain just one, because the rest, they are variations or it's intuitive to understand. But let me go ahead, and then we will see what we could be suitable to tell you. Very important that the most important technique must be presented in this sense. And after that, the rest is clear. Once we understood what is the idea, it's not so difficult to go ahead through, let me say, through the projects, using the projects. Look, let me look at the wording. Model predictive control. Just flesh out this slide. We can see that is a combination, a cooperation, I don't know which word we can use, between basically two concepts. The model, using the model, we can predict the future. Here we can see is written another concept, but nevertheless connected with the model, because the model is detailed understanding, is a detailed description of the system. If next semester you will come to my Kalman filter lecture, you will see that we have also different way to represent the model. Here, when I write here, it's a picture which I don't remember where I found, and a free picture which I found in a control system book related to MPC. Detailed means deterministic. This means that a structured model with consisting of differential equations, parameters, everything which I will show you a little bit in the next minutes. Using this description, this means this model, we can predict And the other, they can predict the future. We will see what I intend. The other aspect, which is necessary in this method, is an intelligent use of the control strategies. And this is the optimization. The intelligent, let me say, control strategies nowadays are considered the optimal control. Why that? Because the optimal control, or in general, optimality, independently of control. I would like to speak a little bit more in general. Optimality means to find a compromise. We are not sure. We are not sure about what could be the best solution. We try to find a compromise between something. No? Also, in our life, if you think sometimes the best solution, the best way to proceed is to find a compromise, to find a trade-off between two situations or more situations. Let me go ahead a little bit more technically. Shortly, we can see that the technique or the techniques, because we have many different approaches. Inside the approaches, we have different variations. Was introduced in the 1980 years, let me say. This means it's relative new as a method. Please pay attention, it works in discrete time framework. But about that, at this moment, I think I didn't tell you. But we will see a little bit very, very quickly what I intend with the term discrete time framework. The line number 3 is difficult for you to be understood because about the control, I didn't tell you in this course. But in any case, I would like to say that in control, we can distinguish two basic methods or strategies. And a feedback architecture, which is heavy, with need to measure the states or to observe the state, to estimate the state. Think about Kalman filter. And the feed-forward control strategy or architecture. And this method here combines. Now, this is written, he overcomes. I copy from a book, I don't like it. But in any case, correct. I mean, integrates and a feed-forward within a feedback. And this is sometimes very easy, simplify the architecture of the feedback because the feed-forward control contributes, in particular in this case, in an intelligent way, to the control. Yeah, the integration of dynamic modeling and optimization, I already told you before. I predict with the model, and then we will see what we can do with the optimization in order to calculate the input to the system. We can include also multivariable problems. Multivariable means I have an input, I have an output, is a single output, single input. We don't have time to do that. No? But believe me, we can also, in this frame, we can also problem in which we have multiple tasks include. Not only one input, one output, but many inputs and many outputs. We can also consider inside this framework to reject disturbance. Disturbance is something which we don't want in the control loop. It's something which deviate our variable to our goal. And we can also compensate in this frame here. Here, basically, with this slide, I would like just to show you colloquially that we can also include constraints. We can see here in the lower bound and upper bound of possible inputs. We will see what is the meaning of the inputs. And look, we have a past control horizon and future horizon, or better to say control horizon. This means the concept of the horizon is something which recall as the prediction. But nevertheless, the past is clear. No, I can store the information which I have basically at disposition from the past history of my control of my system, let me say in general. And of course, this control horizon is something which can be used, but in the sense, in order to use, I have to predict, assuming that this is the present. Now I will come back on this a little bit more in detail. But of course, we can think that I can predict using the model what could happen in the future. And then we say prediction horizon or the control horizon, very often they are the same, but could be also different. But in any case, the prediction horizon is always larger or equals to the control horizon. Makes sense. We will see a little bit in the next slide, a little bit more in detail. Also here, we can see a little bit in a possible draft of the architecture of the controlled system. Controlled means I have a model of the system. The system here is not really is not present, but is intuitive to understand where it is. We have here a system in which I measure something from the system. I measure something from the system. Let me see. And probably could be interpreted a little bit. Yeah, it is to let me say is a little bit this scheme here too compact. I have another better scheme a little bit later. I would like just with this scheme here to show you that we have an optimizer. Probably it's better to speak in this sense, which consists of a cost function. By the cost function, I told you a lot. No? Constraints, about the constraint also, we have seen what is the meaning, and we will see in this context what we can, the constraint, for instance, here we have seen the limitation of the input. I cannot apply 1000 volts in a motor, in a small motor which does not accept 1000 volts or negative volts. No? It could happen. No? Cost function, we know. Using this kind of idea, in any case, I will let me say, I will have an input and a future error between. Let me see, but it seems to be that. No, it's okay. Excuse me. Excuse me. Yeah. That I have it is possible to explain this in another form. Let me start from the model. Probably this is better to understand. I have a model of the system. Now, think about this. Probably it's better to start from here. I have the past input because this I can store without problems, and the past output. Anyway, I have a data. I have a data. In this sense, until now, I can store all data which I need. Using the model, now just roughly, I can predict my output, which is my task, basically. Or better to say, the predicted task, which I will compare with possible reference, which my desired task, to generate errors. The errors in our case is the difference between the desired task and the predicted ones. Also, in accordance of the prediction, I can speak about the future errors, the future discrepancies between what I want to attain, the reference trajectory, and what I have. Using the optimizer, which consists of a const function eventually constrained inside, I will generate an optimal future inputs, not only one, but I will apply just one for the next. It's a little bit extremely schematic. We will come back in a few seconds in more detailed scheme. Here, basically, I already told you exactly. This picture can help to understand what I intended with the reference signal. We can see here these ballets, these blue ballets, which represent basically, we can see here the reference trajectory. I mean, this is what I know, what I want to obtain. If I want to obtain, I have to know. This empty ballet represent the predicted future output. we can see that it could happen that we have a discrepancy between what I want to obtain, the blue, and what I have. Could happen. It happens always. We will see why. And assuming that I have a set point, the target at the end, that is what I want to obtain after I don't know how many steps. But in any case, the goal is the blue. Of course, this, the black dot or the bullet represent what I desired in the past, which I can also use, but in particular, I can use everything which is in the past. This is very important as in a concept, it's clear. We can see also here, I repeated that we have a prediction horizon, which is basically the horizon for my future. And I didn't include here the control horizon because in this slide, I am considering the prediction horizon equals the controlled horizon. Not necessarily they are the same. No, but of course, the prediction horizon is always larger or equal to the controlled one. Now we can understand the concept of the future error, no? Because I can consider in a vector, again, this blue line, the blue dots is in a vector, as these empty dots represent a vector. Let me consider the difference in between. We have 1, 2, 3, 4, 5, 6. Assuming that here I have already 6, 7, 8, tens, let me say tens component in this error vector for the future. Again, this empty is the predicted output. This I basically already explained using the picture. The idea is basically similar to this chess game in which we try to predict our moves and the moves of our adversary. Yeah, here probably is the best way to explain what I already told you, but very quickly and fleshing out the concept. Here we can see a little bit everything in a more clear structure. We have a plant to be controlled in a system, but this is the real system. Could be a motor, could be a bank, could be an economical system, in the sense in a bank, on any economical system, biological system, everything which we want to control, in which we need, whether we have inputs and we have outputs. Again, the disturbances. You remember I told you that this method could be also used to reject, or to control the system even in the presence of disturbances. Now we can see now here what I intend. I measure something. Of course, we will see that to control the system, we need information about all state variables. This means if I don't have information about every states, I don't know if I already told you about the state, probably not yet. I will tell you a little bit later. The states as basically the variable related to the energy of the system. Now I will start with a concrete example in which I will introduce the concept of the state, the concept of the energy, and so on. If I don't have the information about all state variables, I have to use an observer, and therefore I invite you to come to my lecture related to Kalman filter next semester in order to understand what is an observer, in particular this special kind of observer, a Kalman filter, extended Kalman filter. It could be that I will tell you also other kinds of Kalman filters, but in any case, we will see the information about all states. The states are variable which characterize in terms of energy the system, the plant. Could have the presence of noise, but this is just a technical aspect. Using the states, I can predict, and the controller is exactly what I told you before. Basically, consists of the optimizer, consists of constraints. In any case, here inside you can imagine you have the vector of the error. We will see with MATLAB very well, And the controller generate an optimal input or inputs. Why that? Because the output of this controller is in a vector, which considers also the future. But of course, we apply just the present input, and at each step, we will calculate again. We will see that with MATLAB, everything will be a little bit more clear. Here we have a literature you don't need, but eventually we can go in depth for the project eventually in using this literature. But now, let me start with an example, which is an example, of course, it's an example, a technical example for the engineers, basically, but I hope that conceptually I can explain for everybody. Look at this system here. The system here, if you look at the equation 1 and the equation 2, you remember detailed understanding, detailed representation of a system. Looking at the equation 1 and the equation 2, we can see that the system here represents a motor, an electrical motor, even though here we have just the electrical scheme, but which consists in a resistance, which consists in, let me say, an inductance. This means the characteristic of the, let me say, of the stator or rotor. No? If you remember a little bit about the motor, is summarized in this electrical model. R and L represent the physical characteristic of the coils. No? But very important that what characterizes the motor is this U-induced voltage, which basically is the reaction of the movement of the rotor inside the stator. Anyway, this could make sense for engineers, for the rest of students, not much. But think about a mathematical model. It doesn't matter if the system represents the population dynamics. It doesn't matter if the system represents biological dynamics. We have two differential equations, which basically characterize the system which we want to control, in an optimal way. But let me look a little bit together with two equations, even though for not engineers it's a little bit strange. But if you look at the equation number 1, we can recognize, if you don't consider this, for instance, at the beginning, which is we are in the presence of an RL circuit, in which we have clearly the Kirchhoff balance in this equation here. We have the U input equals, if you consider in another form this balance here, R multiply the current, plus L multiply the derivative of the current with respect to the time, because if you don't consider this, for instance, the voltage here is equal what? The voltage here, UR, plus the voltage here, UL. If you don't consider this, of course, if you consider this, plus this voltage here. And if you remember, in Kirchhoff law, I can calculate UR as R multiplied the current, UL as L multiplied the derivative of the current with respect to the time, electrotechnique. This reaction here is a little bit more complex. We can see it here, in fact, that it depends of the movement, as I told you. It's a reaction which we have in the stator because of the movement of the error. But if you are not engineer, forget where this come from. Think about that we can have an equation or two equations. The second equation in particular, in this case, represent the mechanical dynamics, the dynamics of the mechanical system, using the velocity. Here, the first equation, we represented the dynamics of the electrical part of the system using the current. Why we are using the current in the first equation as variable, as state, but we say that is the state variable. In the second equation, we use omega, and we say that omega is the state variable. Because if you remember a little bit, you don't need to be engineer, but in your high school, probably you remember that if you have a coil, you can consider the energy stored in the coil related to the current. The recurrent reflects the energy in the coil. As in movement, of course, the kinetic energy is reflected directly by the velocity. If you don't have velocity, let me say, we don't have kinetic energy. If you don't have current, we don't have magnetic energy. Just really explain in a colloquial way. We can also improve a lot this concept of the state, but the state somehow reflects the state variables, that reflects the energy. The current reflects the magnetic energy in the system. Omega reflects the kinetic energy in the system. We have two kinds of energies, two energies in the system. And concerning the differential equation, I don't know if you know what is the meaning of differential equation. In mathematical meaning, we need initial conditions that reflects in our physical system the initial energy. In any case, we have a relative detailed, do you remember the word, representation of the system? Because we have two mathematical deterministic expression. No? We don't have a stochastic element. If you don't know electrotechnique, it does not matter. But the concept which you have to fix that we have seen here now, how change the current, how the current change, better to say, as a function equals in the sense of the state itself, or states, both, and the input. Of course, everything is in the structure we came from the Kirchhoff. The same here, how change the state omega, the derivatives, if you remember in high school, the derivative represent the changes of omega with respect of the state, in this case, as before, current and omega, but not directly the input, because the input is going to, let me say, influences the mechanical system through the electrical system. We can see that your input influences the current. The variation of the current depends also on the input. And the current is present in the second equation. It is responsible, let me say, together with the state itself, of the changes of the velocity. I can write everything, this information 1 and information 2, in a matrix form. We can see here. This means this information here can be written without losing any component of the information again, and this form here, matrix vector. This means these two elements here, these two initial, this left part of the equalities, the derivative of the current with respect to the time, the derivative of omega with respect to the time, can be considered in a vector. The derivative of the vector of the state variables in the form of vector as a function of this state vector. The state vector consists of two components, current and velocity. This matrix here is the matrix such that, I don't know if you remember the rules, row multiply column. This multiply this, plus this multiply this, plus I divided L multiply U in, I will get exactly this information. To get the second information or the second equation, you can consider row is 2 elements, multiply this 2 elements, this multiply this, plus in algebraic sense, plus this multiply this, plus 0 multiply your input. Believe me, but it's easy to see directly that equals this equation. This means from let me say, from this language here, the graphical language, which reflects the physical system, also this representation is the model, is a graphical model. To this one, it's just a translation. It just, here I use the mathematical language to represent everything which is already, let me say, graphed in this scheme here. But of course, using the Kirchhoff and Newton law. And from here to here, it's just a translation in matrix vector representation in this sense. Again, on the left part, we have the changes of the variable, of the state variables, which is the function of the state variable itself and the input. Initial conditions remain. Here's a possible representation in terms of of block diagram. At this moment, I would like to go ahead. I don't want to comment this here, but we can see that somehow this block is again another language. Sometimes it's useful to implement these equations in MATLAB, in Simulink in particular. And in particular, is extremely important in case we have to do with nonlinear system. But in any case, I will show you a little bit with Simulink. But just for instance, if you consider this part here, just to understand a little bit, just to understand, if this is omega, here we can consider omega dot. Here is a little bit not exactly correct. This omega dot is and this position here. I don't know why it's moved, but it's clear. No? The output omega is the integral of omega derivative. No, of course, in the integral I have to consider the initial condition. In this sense, the initial condition. But the initial condition in Simulink MATLAB is easy, for instance, also the tool to put inside this block, which is the block in Simulink. We will see. I don't remember if I simulated with this form here, because we have in a linear system. It could be that I use another block. But in any case, just to understand that the integral of the derivative is omega in this sense, of course, plus the initial condition. We will start from the initial condition, then I integrate, I go ahead. And what we have here, we have is not omega dot. Omega dot is here. Here, basically, if you think that this is the current, multiply this, realize the multiplication of this signal by this constant here, which is the signal which basically we have here. Km apostrophe divided J, multiply the current, minus Kf apostrophe multiply omega, which is here, no? Of course, divide J, no? Represents the second equation. I don't know if it's clear. This language here, or this way to represent in the dynamics, represent basically the second equation, the second dynamics. Just to show you how we can explain a little bit this language, which at this moment we will not use, but could be useful for the project. It could be. It could be. But it's extremely intuitive. Please pay attention that this omega dot is here, let me say, close the integral block. It's intuitive to understand that the arrow represents the flux of the information, represent the signals. But let me go ahead with more mathematical aspects which can help us to understand the prediction. At least today, I would like to introduce the prediction. Equation 1, equation 2, I try to explain very quickly. For not engineer, it is clear, it's a little bit obscure, but don't care about that. You have a mathematical representation. I think in your courses, you had the differential equations, probably not so in depth, but you know what I intend. Now, do you remember one of the characteristics, one of the, remember I listed 5 points at the beginning. I told you that the MPC, the model predictive control, is conceived inside a discrete frame. You remember this? But what is the meaning of discrete? Yeah, let me show you a little bit what is the meaning of continuous, not discrete in this sense. The meaning here is the time, the variable time, is in a continuous variable, not only continuous, uniform continuous variable. This means t change continuously, the time. we can intuitively understand. Discrete means that the time, I try to explain this concept in a colloquial way, not just intuitively, that the time does not change in this sense. Let me explain better. The time change always continuously, because otherwise it doesn't make sense. Let me explain better. But the function which depends on the time and the continuous representation change over time continuously. For instance, here the current. Once I started, probably at the beginning it could happen that it's not exactly continuous, but then if something strange, let me say, does not happens, no impulse, something, we have the current change over time continuously. Let me see if I have a picture in order to understand, because I know that this concept here would be difficult. In discrete, the variable, state variable, was any kind of variable. In the system, it could be that we have also other signals, not only state variables. We will see a little bit later disturbances or parameters which change over time, which is a function in any case. Let me now switch on the lateral camera in order to intuitively show you now let me take something to indicate what I intend. Now, colloquially or intuitively, we can see directly what I intend with the term discrete variable, state variable, not only state variable, any kind of signal or the variable which can change, not more continuously. We can see this blue line and continuous function. I don't know if you remember the concept. Here we have something which is not exactly continuous, stepwise constant. I mean, of course, in this interval is continuous, but of course, is stepwise continuous. Clear, no? What I intend. I mean, here we lose the continuity. And we say that if the phenomenon or the variable f of t, of the function f of t, is represented in this way, in this stepwise continuous form, using steps, we are in the presence of the discrete or discretized f of t. It's a little bit intuitive, the intuitive idea of the discretization or a discrete variable. Why I speak about discretization? Because in this particular case, you have a continuous model. And then exactly now, I will try to explain that using this method, the discretization, the name of this method is forward-Euler discretization, we will obtain a stepwise constant model, or well, let me say, discretized model. Look here. If I consider the current, which is a continuous function, typically, which is something we change continuously over time. Keep in mind that the picture which I told you, the difference between a continuous f of t and a stepwise continuous. Oh, yeah. Or stepwise constant also, because at each step is constant. If you consider this position here, in which k is a counter, as a natural number, and please look from here to here, I neglected the s because if the s is fixed, it's a little bit an informatic language. basically, when we have the vector, the current, we don't need TS because it's including also in the vectorialization. Anyway, mathematically, you can consider this expression here equals this one because TS is given. Very important that I have that each K, the corresponding I. I do the same for omega. I do the same for all signals, let me say, we change over time. Now about all signals, we have to be careful, but at least in the model which I presented, all signals. Then we will, next week, I will go a little bit more in depth on this. I will approximate also the derivative in this form. Probably you have seen this in high school, no? The derivative of the current, the derivative of omega. What is the idea here? Ts is the sample time. What is the sample time? We have seen here, no? This interval here, which is at this moment, let me say constant. Again, continuous function of the variable, state variable, stepwise continuous, or stepwise constant, no? In the sense, in this interval is constant, but the change also. The interval is constant, but change. Stepwise continuous, we can say. But we can understand very well that inside this TS, I don't have a variation of a system which basically intrinsically changes, but the information will update just here at each TS, or if you want, at each K, no? Because TS is given. With K, we can get the information here, the information here, the information here, which is the level, let me say, at the corresponding time of the function O. In any case, the physical function, which we call the inputs or output or moreover states. The method the name is forward Euler, because basically we are considering, we can see here, the present at k minus 1 and the future at k. This means the derivative is approximated with this method here, forward, future minus present, divided the interval which I consider, for instance, 1 day. But could be also 1 millisecond, 1 nanosecond, 100 years. Depends on the system which we want to control. How fast is the system? No? If I want to control the movement, to observe, in this sense, the movement of the galaxy, of course, this TS must be very large. I don't know, 100 years, something like that. Otherwise, I don't see what happens. Of course, if I were to describe an electrical system and a motor, this could be, it depends, of course, on the motor, but nanosecond, microsecond, millisecond, also second, this depends. How fast is the dynamics? Of course, for not engineers, it's a little bit strange, this language, but anyway, the concept of the model is, I think, is clear. Now, if I plug in this information here in the lower part of the slide, here in this equation 1 and 2, believe me, just plug it in as in gymnasium. I will obtain equation 1a dot and 2a dot. What these two equations are? These two equations represent the discretization, or better to say, the discrete dynamics of the given system, in accordance to, again, forward Euler method. We have many methods. For instance, there is also backward Euler, no? But there is also many other methods with different characteristics. What is the best? No one is the best. This means it depends on the system. I don't have time to go in depth on which kind, or let me say, to consider the discretization methods, but we have many discretization methods. Very important here to notice that now the current and omega depends again on current and omega, the previous current and previous omega, as here, no? The current at time k, let me say now, depends of the current before, omega before, and input before. Of course, we can represent it also in different form. let me go ahead here. Very important to notice that now we have a TS, which is inside the equations. Why that? Because it's clear that TS influences the dynamics. I mean, if I consider a TS twice of this, we have the longer interval in which I don't have information about the system, in this case about the signal, because I will receive information just here instead of here, if I consider instead of TS, 2 times TS. This is clear, represents a big difference, not only for f of t. I mean, here I have a vector which represents f of t, which is characterized by this level, and this level. After 3 times, let me say, TS, I have these 3 elements. But of course, if I consider twice, I have a more rough representation of f of t, because I have this as before, but I don't have this. This means, of course, the representation is totally different. Let me say now colloquially, totally different. In this sense, we can understand very well that we have a different way to represent the signal. We can say, if I have just a signal, we can say that if TS is very small, I have a more precise representation. No problem to understand. If I consider half of TS, I have more elements to represent f of t. This means I have a more precise. You did in gymnasium, in high schools. But do you remember I told you that in different dynamics, I didn't consider here the word signals, even though the signals are in the dynamics. We can see the current, we can see omega, but at each time, in the dynamics, the situation is totally different. If you consider TS is very small, not necessarily we have a better dynamics. I will clarify a little bit later, but we can see also from here, if TR is very small, let me say 0, we can see that IK is equal to IK minus 1, because TS is 0, or almost 0, TS is 0 here, TS is 0 here. This means we destroy the dynamics of the system. Very interesting, this effect of TS. I will come back on this. It seems to be that statically, each signal is better represented. But here we don't have the whole signals. We have the signal each time. In this expression here, it seems to be very small. TS destroyed the dynamics, because if I say that IK is equal to IK minus 1, we can see also here this omega k is equals omega k minus 1. We don't have dynamics. I cannot represent the dynamics. Not only here, I cannot control, because I annihilate the effect of the input. Please pay attention. Here is the model. We are speaking about the level of the model. But of course, the model must reflect, the dynamics, must reflect, let me say, the real system. But if TS is very small, we can see that the dynamics does not reflect the real system, because the current change over time. If TS is very small in this context here, we don't have these changes. We will come back on this. This means keep in mind that the model depends on TS. TS should be not so small, but of course should be not so large. We will see why, but so large is intuitive. No, otherwise I lose what happens between one measurement and another one. One prediction is another one. Few minutes, I will introduce the prediction, and then we will conclude for today. Next week, we will conclude the lecture, and we will simulate with MATLAB. And we will understand probably a little bit better everything. Look, as before, these two equations, equation 1a dot 2a dot, I can, let me say, summarize, why not? I can reorganize in terms of matrix and vector. we did this exercise in continuous. We can do the same in discrete. The thing which I did here, I considering not k starting from 0, but k starting from 1. This means we don't have here k plus 1 on the left, but we have a k. I don't know if we can see also. No, in this lecture, is direct understandable. Is direct understandable. Here I have to explain exactly what I am trying to explain now. But let me remain here. And then I will come back on this case. This representation here is exactly in other ways, as I explained before, to represent 1A and 2A in terms of matrix and vector, in which we have the actual vector. In the model, this means hat. Let me say predicted. Why I'm introducing now the concept of the prediction? Because the present, if this is the present, is a function of the past. State, vector, and imp could be on the vectors of the imp. Typically, we say this is the future. Otherwise, what? Okay, the concept of the prediction is nevertheless there. But anyway, it's more natural to think this is the future. Tomorrow is a function of today's states. The tomorrow states in the function of today's states, plus what I do today. Makes sense, no? Of course, in this frame, which is the model, discrete model. Let me consider now that I want to predict not both states. I can do. Also, here's a prediction. I explained. Again, the state vector tomorrow, characterized by ik omega k, is a function, complex, not complex, in this case, a linear function, using the matrix, of the state vector of today. K1 is today. Remember, we started with this. Current t omega t is a function of k minus 1. K minus 1 is today. If I want now to control the second variable, for instance, the omega, but I can control both. It's not just the problem. But let me simplify a little bit also the notation. And considering now, instead of k equal 1, starting from 1, but starting from 0, we can see that here I translated everything. I don't know if it's clear. This x hat k, hat means model, prediction, becomes k plus 1 if I start from k equal 0 instead from k equal 1. It's easy to see. No? From k equal 1, we have I of k. If I start from k equal 0, I have to have also here I of k. Or x hat of 1, we have also in this representation. Typically, we are working with this in the books. I copy from books, not my invention. Yeah, again, hat means prediction. No? Prediction based on the actual value of the system. I can measure current and omega. We will see in Simulink, in which I measure current and omega. Each time on the present, we will see now in the, I have just one slide to show you. 2 slides, the last 4. X without hat is what I am measuring, or what I am observing with an observer, with an estimator. U again without hat, because it's what I am measuring. X vector I am measuring, or I use an observer. If I cannot measure, we will see next semester what an observer is. And U is the input, which is basically is always available because it's the output of the controller. Now, the second equation is exactly what I wrote here. Of course, starting from k equals 0 is the omega, assuming that I want to control the omega. What is CK? What AK is written here? What is AK? What is BK? Is the discretization of the matrix A and the matrix B. Here, the discretization of this matrix here, it itself. No? In this system here, it itself, because does not depend, this equation here, on the past. No? We have everything is in a function of k minus 1 left, and anyway, we have on the left k minus 1, and we have on the right k minus 1. We have the same timing in a sense. Again, here we have the control horizon, which is basically in our system equals to the prediction horizon. Could be also different, but again, the control horizon is less or equal to the prediction horizon. The last slide, and then next week we will conclude the presentation. The system now is known. I already clarified that also here is in a prediction. And we can see explicitly, not only for the both states, the prediction of the omega, including C. I have the omega here, the predicted omega. Why that? Because this expression is here. And basically, this expression here is this explicit form of these two information here. Is there already in a prediction in the model? Of course, in the discrete model. And here we have an explicit omega. Let me see the step ahead. Again, k plus 1 now represent tomorrow, no? And k represent today. We can see that the omega tomorrow is a function of current and omega today and the input today. Now, if I apply recursively this concept here, I mean, if I add here 1, this means y hat k plus 2, y hat k plus 2, you have here x k plus 1, u k plus 1. And then if I apply, again, if I plug in basically x k plus 1, which is here, believe me, next week we will reconsider a little bit more in depth, believe me, we will obtain this, is easy to see. And this remain because it's exactly this in which I add k plus 1. And if I go ahead until P, which is our predictive horizon, I will obtain this apparently complex expression, but it's basically the result of the successively substitution. K plus 3 means here again k plus 1, k plus 1, k plus 2, but of course, k plus 1, x hat k plus 1 is still this one. And if I reintroduce this, I will obtain, I did input y hat, the predicted, time after tomorrow, if you want. And then in this page here, we have already an explicit expression based on the detailed understanding, you remember, the detailed model, which is represented by the matrix A, the matrix B, and in this case, the matrix C, just a selection of what I want to predict. But the matrix AK, this BK, are both the detailed understanding or representation of the physical system. Next week, we will start from here. I am sure that I will be able to, because we have just at the beginning of next week, a little bit to understand a little bit some formal aspect. This is a little bit a difficult form for next week, the particular cost function which we want to consider, but at least the cost function, it's something known, which I explained before. And then, of course, we have to speak about some technical problem. And you remember this concept here, this gradient, we will see next week, which is basically is a necessary condition to find an optimal solution, but becomes sufficient in case the problem, please pay attention, we will see next week, is a little bit more difficult. The problem is a convex one, as in the case which I present in this course. This we will see together will be the solution calculated offline. We don't need an solver. We don't need the solver in this particular case because the problem is solvable analytically. Because the problem is solvable analytically. The reason is the problem is somehow convex, but it's not enough convex. We will see this in particular form also of this function here. Basically, we don't need, at least if Q and R, we will see together, are given, we don't need a solver. We don't need PSO. PSO isn't a solver, remember I told you. Or other kind of other kinds of solvers. We will see next week this, and then we will, in any case, simulate the basic form of MPC, and through the MATLAB, I will come back on this block diagrams, we come back on the concept that we have to measure or to know somehow using observer the actual states, xk. And now was a little bit an introduction, but I already presented the structure of the prediction. We will restart from here. No? Now I flesh out a little bit, but it's a mathematical, relatively easy structure, no? to plug in basically the future. It doesn't matter how far away is our future, always as a function of the present state, or the state vector, and let me say the inputs, particularly the inputs of today, but also the input which I intend to calculate tomorrow. The meaning intend means something in the future, and I will go a little bit more in depth on the concept of the input, because we will calculate using this method all inputs, optimal inputs. We will see how, but I will apply just the actual one, and at each time, at each step, I will redo the calculation. I will redo, because it could be that change some conditions. If it doesn't change anything, I don't need to redo, but we will see that in the presence of disturbance, you remember this. Of course, we have to, if I want to predict what I will do tomorrow, probably is enough to do in a calculation today. Of course, but if I want to predict tomorrow and after tomorrow, it's more convenient tomorrow redo the calculation, because I don't know what happens between today and tomorrow. This is a little bit the concept. Therefore, we will recalculate. We will redo the calculation. What is redo, we will see next week. But it is enough for today. Next week, we will see also the simulation. Let me conclude now. I'm here for questions. Otherwise, we will see next week, and think that we will continue 1 week more to recover the lecture because I need the lecture at least to use this time to discuss project. We will see. We have how many lectures until now? Let me see, until the end. I think we have in any case next week. I don't know if after next week, the 8th, I don't know if the 8th is lecture. It could be 8th is lecture time. If it's not lecture time, we will do it is, yeah? It's a normal lecture time. Yeah, this means we will continue until 15. I mean, continue. We will meet also 15 to recover the lecture of last week, because I was not able to be present. So we have a time to do MPC, to discuss MPC. It could be that I will introduce also a little bit the recursive least square, but MPC is more important in the sense. And then on 15, so we have the time to eventually to discuss your project ideas, or to repeat some concept in MPC or in recursively square. I think it's a good program in any case. I have to do. Okay, let me conclude now. The material is there, what we did together. And thank you to be here again. Excuse me for my being late, but at this moment, the situation a little bit so sometimes for personal situations, and sometimes in other course for I am involved in some boring administrative meetings. Thank you.